remark, and I will leave you things to you guys. So my name is Qiao, and I'm a faculty from Xiamen University, China. And this is the 16th, overall the 16th meeting of our SIGCOMM Paper Reading Group, and the first one after the summer break. So I hope everyone is had been enjoying the summer. And because we are 1 month away from this year's SIGCOMM, so before the official before the conference, we will have 2 meetings, including the one today. So for these 2 meetings, we will read papers from this year's NSDI. So it's sort of like a pre-opening for the SIGCOMM conference. So I think after the conference week, we will switch back to focus on papers from this year's SIGCOMM. I'm sure there are lots of many exciting and interesting papers over there. So today, we're going to read the paper called eTransport, Extensible Kernel Transport with eBPF. The title really explains what this paper does, but I'm sure there are lots of clever ideas and details that we will read and understand together with the presentation and the discussion. So the presenter would be Wang, a graduate student from Xiamen University, and we also have the honor to invite the first 2 authors, Zhongjie Chen and Qingkai Meng, from Qingkai University and Nanjing University, as our guests of honor. So as usual, we will have Yao to give the presentation for about 25 or 30 minutes, and then we will follow up for another half an hour live discussion with our guests of honors. So without much further ado, so I will give the floor to Yao. You can get started.
Okay. Hello everyone. I'm Wang from Xiamen University, and I'm a master student now. And today we're gonna learn this paper, eTran Extensible Kernel Transport with eBPF. This is a joint work from Qingkai University, Nanjing University, Harvard University, and UC Berkeley, UC Davis. And this paper is focused on enabling fast and safe and customizable transport protocols directly inside the Linux kernel, and without giving up the protection and operational advantages that comes from staying in the kernel. So let's start with the background. Over the years, the data center transport protocols have evolved in many dimensions, from different semantics like string versus message, to congestion control styles such as the sender driver or receiver driver, and also loss recovery strategies like SSKs or packet trimming. And the data center workloads has been more diverse. Think of the latency sensitive microservices, throughput hungry storage, and large scale ML training. The problem has occurred. There is no one size fits all transport that works best for all workloads. So we know that both industry and academia has been continuously proposing many excellent protocols to adapt to different scenarios like TCP or TCQCN. However, most of protocols have components running in the kernel, and involving kernel transport has taken a long time. So why it's so hard to innovate inside the kernel? There's three reasons. The first one is the development and the maintenance efforts is heavy. The kernel code base is so complexity and contains of thousands of codes to review. And the second one is the performance often lags compared to the user space stack, bypass stack. But the last one is even if you have finished your coding, your programming, you still need to take years to upstream the changes. It may take years for a new protocol to be accepted to the mainline kernel. Like TCP took 4 years, and MPTCP near decades. So as a result, many designs stop at the kernel bypass protocol stage, great for experimental, but not deploying the kernel itself. You may ask, why not stick to kernel bypass solutions like DBTK or RDMA? Well, the bypass stacks can be very fast, but they have drawbacks. For example, the library OS approaches gives directly access hardware access, but raise serious security concerns and will dedicate hardware resources to a single app. And like microkernel style approaches can improve isolation, but performance is only moderate, and they require implementing the stack from scratch. So the question is, can we achieve agile customization, kernel safety, strong protections, and high performance all at once? There is an existing answer with eBPF, the extended Berkeley package filter. It lets us run verified code safety in the kernel at runtime. Over the last few years, eBPF has transformed the subsystem from networking to observability. With XDP and AF XDP, we already have fast kernel and user space package processing, but there is still gaps when it comes to full transport implementation. There's two major challenges. The first one is full transport logic like TCP states machine is still too complex to eBPF program models. Even if features like dynamic memory and K-funcs have improved since. And the challenge two is XDP today only work for ingress traffic, and you can send the package proactively, and there's no native queuing or pacing mechanism. So the first big design idea in eTran is to split the transport into two distinct planes. The first one is control path. This is a root privilege daemon in user space, and it's in charge of heavy lifting tasks that do not fit well in eBPF. For example, like setting up and tearing down the connections, running congestion control algorithms that require floating points math or complex data structures, and also like handling timeout based loss recovery. And the second one is data path. This runs in kernel, but in a safe and sandbox eBPF environment. It handles the performance critical package by package processing, like validating headers, managing sequence numbers, generating SKs or credits, or applying pacing. So why eTran do this? This is because eBPF is powerful, but has constraints, like no floating points, limited loops, or bounded execution time. So by pushing complex logic into the control path, and keeping the data path lean and predictable, we get both best of both worlds, safety and speed. The unprivileged app only interact with the lean library for tasks like segmentation and reassembly. This library cannot touch the kernel transport state directly. So even if it's buggy or compromised, the core transport the core transport logic is still safe. The second design idea is about extending the eBPF XDP subsystem, so that it can support full transport functionality, and not just package filtering. This paper introduces 3 new building blocks, 2 XDP hooks and 1 eBPF map. The first one is XDP egress. Today, XDP is only for ingress packages. With XDP egress, we can intercept packages right before they leave the NIC. That means we can fill headers from kernel protected states and enforce flow control or applying congestion control checks before the transmission. If the package isn't allowed to go out here, we can redirect into a pacing queue. The second one is the XDP gen. This is a package generator hook. Many transports need to send the package proactively, like ACKs or credit grants. Even when there's no incoming package to trigger, the XDP gen runs at the end of the NAPI pool loop and can bench list control package effectively from pre-allocated buffers. The last one is the PKTQ. This is a new eBPF map type designed to hold package pointers in time order buckets. Paired with extended eBPF timers, it gives us precise pacing, and you can do rate-based pacing or for TCP or credit-based pacing for home. Next, let's dive into some detail about them. Both XDP egress and XDP gen are designed to feel familiar to developers that are already using XDP. They use the same XDP MD context structure and same styles of written codes and most of the same helps. And that means you do not need to learn a new programming model. This paper still keeps safety guarantees. The verified ensure bounded loops and it restricts available help so that you cannot, for example, arbitrarily look up sockets from within this hook. The next one is the PKTQ. Is the heart of the pacing mechanism. It is essentially a set of time buckets, like a timing wheel. Each holding points to pre-allocated package brands. The eBPF program inserts packets into the bucket corresponding to their scheduled send time. And then the eBPF timers then trigger callbacks to join the right bucket at the right moment. They work both for the rate-based pacing, like leaky bucket for TCP, controlling package per unit time, and also credit-based pacing, where a receiver grants credit to a sender, as in Homer. Because everything in the eBPF, it avoids context switch between the user space and kernel space, and so it can sustain very high package rates. So now let's zoom in on an important part of the design, the performance optimization. These hooks like XDP and egress and XDP gen are in the fast path. So that means like runs for every packet, and any efficiency here will be magnified at a line rate. So eTran put a lot of engineering work into making them as lightweight as possible. First, you use pre-allocated memory pool. In normal kernel code, you may allocate the memory for each package package structures on demand. But in eBPF allocations in fast path can be costly and unpredictable and can even fall under load. So our approach is to allocate all the package frame structures we need ahead of time at setup, and then simply reuse them. This completely removes the need for allocation in the hot path. The second one is it is aggressively bench operations. Instead of processing each package in isolation, we process multi-package in bench per NAPI per cycle. And let us amortize the cost of helper functions cost, reduce instruction overhead, and improve the cache locality. The last one is it apply minimal helper exposure. The eBPF programs at these hookers are only allowed to use the essential helps and can function for transport processing. This keeps the attack surface small and make verification faster, and prevents essential misuse of kernel resources from within the hook. The combined efforts is lighter, faster bus paths, lower per package overhead, fewer cache misses, and the ability to sustain high throughput without compromising safety. Let's look at how all the pieces fit together. An application talks to a user space library, and this handles the segmentation for send and the reassembly for receive. And then the queue management AF XDP. Importantly, it has no access to the transport states inside the kernel. So the control path daemon runs with root privilege and manage all the sensitive transport logic like flow tables, congestion control parameters, loss recovery decisions. When you need to update this, it uses the shared memory with eBPF maps for low overhead communication. On the data path, packages enter the XDP egress hook, and where we validate the update states and possibly generate a control package where XDP join. On the way out, the XDP egress enforces pacing and send them to the NIC. It also uses virtual AF XDP sockets to scale across the multi-hardware queues. This is critical for multi-queue. Let us achieve parallelism without losing isolation. Okay, next, let's briefly go over some extra features of eTran. One of the big advantages of staying in the kernel is multi-tenancy. In eTran, it can isolate resources at the queue level. Each app can be assigned its own AF UMem and its own API queue and its own pacing queue. And this prevents one app from monopolism NIC bandwidth, which is a real problem in some DPDK-based deployments. Finally, because the hook is programmable, so we can chain additional policies into fast paths using the BPF tailcall. That means you can load traffic monitoring, ACLs, or places rating rate limiting modules at runtime without touching the transport logic itself. So it is an easy way to adapt operational needs without sacrificing performance. So to demonstrate the extensible of eTran, there's two cases. The first one is the TCP. It's a connection-based and the string semantics sender-driven CC congestion control and expose POSIX socket API. The second one is the home, a connection-less follow message semantics use receiver-driven congestion control and provides an RPC style API. And these two examples implemented with 2 kilolines of kernel and about 7 kilolines of eBPF codes, and with 13 kilolines of user space codes. For evaluation, this paper chose the Linux experimentation of Home Linux TCP and the TAS. The TAS is a high-performance kernel bypass TCP IPI stack. So the result is here. In RPC workloads, eTran Home deliver up to 4.9 times lower P99 latency for large message, and for 3.6 times lower P50 latency compared to the Linux Summer. The receiver-driven congestion control logic was implemented entirely with XDP join and packet decree. Enforced SPRT scheduling without breaking safety constraints. In the KV store workloads, the eTran DCTCP achieved 2.4 to 4.9 times higher throughput and up to 3.7 times lower P50 latency than Linux TCP. For the loss recovery was enhanced with both fast retransmission in eBPF and the timer-based triggers from the control path, and without locking between the planes. Even if there is slightly slower than TAS, but eTran retains the kernel safety. And to wrap up, the eTran delivers strong protection, kernel safety, and driver customization and high performance. It achieves this by extending eBPF with new hooks and maps and hiding transport states inside the kernel, and borrowing provenance techniques from user space stacks. It makes the kernel a viable playground for transport and innovation again. That's all. Thank you.
Good. Yeah, thanks for the great presentation from by Yao. So next we will move to the discussion part. We have great honor to have the authors, the first author and second author, Zhongjie and Qingkai here to share their insights and experiences about this work. So does anybody online have questions? You can just say it in the Zoom or type it in the chat box.
Can I ask a question first?
Okay.
Sure. So I think the Yao, can you go back to the slide showing the two case studies, HOMA and DCTCP? I think slide maybe number 17. Maybe one more, 16. Yeah. Well, yeah, this one. Yes. So I'm curious, like how easy is it to use eTran to implement a new transport protocol? The reason I'm asking is I'm looking at the essentially the eBPF code it takes to implement the DCTCP and HOMA is approximately 7.5K length of code. So so is it but I thought I may be wrong, but I thought like eTran essentially provides lots of different hook functions and a certain interface or certain helper libraries to enable user or developers to implement transport in eBPF. It's supposed to make things easier, right? But looking at this number lines of code, is it easier or actually it's still pretty complex? You still need to do a lot of like handcrafting to implement different types of transport protocols. So
yeah.
and for Zhongjie, please, thank you.
Okay, thanks to Charles' question. That's a good point. I would say making implement transport easier is not our target. Our goal is to offload the transport logic into the kernel to benefit from some advantages of kernel like security, protection, resource multiplexing. That's our goal. Our goal is not to make implementing the transport much easier. Honestly, implementing DCTCP and HOMA is not very easy, especially the HOMA transport, because its congestion control algorithm is very complex. And I did made lots of effort to implement HOMA. But I think after we implement the basic transport like DCTCP and HOMA, user can use our template transports for future customize. Yeah, that's all.
Yeah, I think it depends on what kind of transport or congestion control we want to implement. If we want to implement some congestion control like TCP variant congestion control, maybe we can easily since it just need to revise some AMD function, and it can be easily add to our sender driven CC. And if we want to use if we want to implement some HOMA like congestion control, maybe we can follow the HOMA platform we implemented in our eTran. But for other different congestion controls, maybe we also need make a lot of efforts to implement.
I see. So I know there are probably over 100 types of different transport protocols proposed in either papers or open source or even just a class project. So what's the limitation? Yeah, so sorry to holding the microphone too long, but what's the limitation? For example, or in other words, is in your case studies, I'm sure you read many papers, data center transport, right? So what sorts of transport protocols would be extremely hard or maybe even impossible to be implemented in the current design of eTran? Have you thought about it or studied this, or you just pick maybe some most representative? I see these two case studies actually very thoughtful, right? A connection-based versus connectionless, and stream semantic versus message. I see the reason you pick these two is you want to cover different aspects of transport design. But as a non-expert in transport protocol, so any fundamental limitation, for example, could you implement HPCC using eTran or other protocols?
Yeah.
What's the limit? Yeah.
Actually, we have some discussions in our appendix to discuss if eTran can implement more transports, like you said, HPCC. I think the short answer, I think, is yes. eTran can implement more transports because the first design of eTran is to split all transport logics to two parts, and the functionality we summarized, I think, is very common for all transports. For example, segmentation, reassembly, pacing, rate limiting, and congestion control, loss recovery. I think all transports need these abstractions and functionalities.
I see. Okay, yeah, that's I think that definitely helped me understand this better. Cool. All right. So I have a couple more questions, but I think Monray already typed 3 questions. She has been waiting. So I will Monray, maybe Mingray, sorry, Mingray, you can either speak or you can just let Qiang read your questions. Yeah, please.
Yeah, okay. Let me just read the question. So we have an audience in sharing his questions in the chat box. The question one is, what is the key difference between eTran and other user space transport libraries such as Meta's MVFast? And the second question is the upstream has a BPF struct option for BPF-based TCP congestion control. Is it possible to reuse the upstream TCP congestion control in eTran? And the last question is, have you received some feedback from the Linux kernel community on this extensible BPF? Yeah, so Zhongjie and Qingkai, do you have any ideas on these questions?
Yeah, let me answer the first question. What is the difference between using eTran and user-space transport library? Okay, I think the key difference is that the core transport logic is located in the kernel in eTran. And untrusted user space library cannot have a direct access to these transport states because it is protected in the kernel. So I think eTran is more have a better security attribute than other user space transport stacks. And user space yeah, I think this is the main difference. There are many other differences between eTran and other space transport library, I think.
Yeah, I think the user space transport library always need pruning, right?
Yeah, they usually use pooling to achieve high performance. Yeah.
So they always consume a lot of CPU resources compared to
yeah, that's another difference between eTran and other user space transports because eTran is essentially interrupt driven. That means the transport logics are handled in the kernel NAPI context, which is a pooling and interrupt combined approach to process network traffic. And that means eTran can have, eTran doesn't need to monopolize a CPU core for pooling and thus wasting CPU circles. And eTran is much, and thus eTran is much more CPU efficient. Okay. The second question is, upstream has a BPF struct ops option for BPF-based TCP congestion control. Oh, yeah, I know it. Is it possible to reuse the upstream TCP congestion control in eTran? Upstream TCP congestion control in eTran. Okay. Struct ops is designed, BPF TCP, I think, is designed to allow users to customize congestion control in TCP. But eTran can do more. It can allow users to re-implement all transport logics. In addition to congestion control, eTran can implement loss recovery and many other things. So I think, yeah, the answer is yes, we can reuse the upstream TCP congestion control in eTran as long as we implement the TCP congestion control logic in some several hooks provided in eTran. The third question is, have you received feedback from the kernel community? Okay. Actually, we haven't communicate with the Linux kernel community to discuss the feasibility to merge eTran into the Linux kernel. I know this is a very challenging process. Yeah.
Yeah, cool. Thanks for the question. And Actually, following the first question of Ming I have another question. Yeah, so I noticed that Google has proposed a user space stack network stack design in their SOSP paper. The system is called SNAP, SNAP. They decouples the network stack into multiple user space modules and collect them together to make modular network stack design. So they also claim that this design can accelerate their improvement in in the network stack in their cloud, as well as high performance. So, do you think actually your paper shows another way to customizable network stack? So, do you think which one is more practical in future clouds, especially private clouds?
Yeah, okay. Actually, the latest news, I heard that Google doesn't use Snap anymore.
Okay.
Yeah. This is the latest news I heard. Regarding the question that which one is better for future clouds, especially for private cloud, I think there are many trade-offs between the systems. For each one does need some kernel modifications to make everything work. But I think as long as we apply these changes to the kernel, users can benefit from the benefits of each one. For Snap or other stacks, I think there are really many advantages of these systems, but I think these systems need a huge team to maintain and build the system, which is not feasible to all companies or users. But the kernel is out of box and everyone can use it directly. And as far as I know, Google has not open sourced their Snap.
Yeah, I
Okay.
know that. Yeah, that makes sense. So
I also have some questions. Maybe only one question. From the previous discussion, I know that the kernel modification, the code for the kernel modification and the user space codes can be reused or can be a template for other protocols implementation, right? So the system contains two codes, the user space code and the kernel space code. So could this make it difficult to integrate it to the Linux mainline? Because I mean, it is easy to maintain the consistency or stability between the two during the updates. I mean, the kernel updates reading the user or just the kernel updates may make the user code unusable. So it is easy to use.
Yeah, I think this is a general problem for all systems that have two paths located at in user located at user space and kernel. I think the key to solve this problem is to define a good interface between the user space and the kernel. So if this interface is well defined, even if we make some changes in kernel transport, there's no need for the user space library to apply some code changes.
Okay, yeah. Thank you. Got it.
Cool. Yeah. Another following question. So I understand that in private clouds there are many kinds of network stack, including the user space ones and kernel TCP/IP stack, and as well as some hardware and software co-design network stack. They are both okay because they are in private clouds. The network stack will be safe or will be always safe. And in the public clouds, to customize the network stack, the most important thing is the security, right? So I'm just curious that in the public clouds, why the tenants need to customize their kernel stack? So basically, we always use the default TCP/IP stack, right? So why do tenants need to change the transport?
Yeah, good point. So the question is actually ask what's the motivation to customize transports for public cloud tenants? Yeah, I think the network extensibility is very important because for certain workloads, we need more smarter and advanced algorithms to handle them gracefully. For example, an incast scenario. We all know that the standard sender-driven congestion control algorithms cannot handle incast traffic gracefully. However, the recent proposed receiver-driven congestion control algorithms can handle the incast traffic very well. So I think this is a motivation for users to change the standard sender-driven congestion control to smarter and advanced congestion control to make their workload run faster.
Yeah, okay.
I think I can complement some point, and I think for even for the tenants that rent the server in public clouds, like they would like to like achieve minimal latency, like for Kiwi Cache application, like then tenants would like to use like kernel bypass techniques to accelerate their host side packet processing. And also they would like to use like what Zhongjie said, like to optimize their congestion control, like for their specific traffic pattern to enable high performance in network transmission. So we can see that tenants need customization for maybe for high performance.
Okay.
Yeah.
I think this is pretty tricky as tenants always do not know the underlying network infrastructure, right? So to providing high performance congestion control is the labor of I think it is always the work of the clouds, the cloud providers, because they always know the underlying network infrastructure. They have the view and the ability to optimize the for example, the congestion control. But for tenants, they can only know their virtual machines, right? So I think there might be a big limitation for them to customize this transport protocol. So I think it is a little bit tricky.
Sorry, I don't fully second you, because I think only the users know which applications they want to use. So for different applications, different workloads, we must carefully tune the algorithms for them. So
Okay.
however, this knowledge is cannot be achieved by the cloud providers. Yeah, only the users know which applications they want to run. Yeah.
Yeah. So the transport here is probably application specific, right?
Yeah.
Yeah, that's
Specific.
what we want to
that
say.
makes sense.
Even though yeah.
Okay, cool. Yeah, we got another question from the chat box. How does eTran? Yeah, Bing, please go ahead.
Oh, okay, thank you. My name is Yang from Southeast University, and my question is about the design principle of the eChain. And we know that the protocol stack have multiple protocol, and for example, the IP protocol and the link layer protocol. And my question is, how does the eChain deal with the lower layer protocol and lower the transport protocol? And how does it get these resources? For example, how does the eChain deal with the IP protocol? How, for example, get the routing table resources, or for example, can eChain reuse the capability provided by the kernel, like the IP tables, or the lower capabilities behind the transport protocol? This is my question. If only protocol
Yeah, that's a very good point. Yeah, very good point. Yeah, that's the advantage of eTran is eTran can leverage the existing kernel infrastructures. For example, the routing tables in kernel can be directly used by eTran. Actually, in the eBPF code, eTran can call some BPF helpers, which is already provided by the kernel, that eTran can call these BPF helper functions to look up routing tables in kernel. And so there's no need for eTran to implement low-level protocols that is relatively fixed compared to the upper layer transport. Yeah.
I think.
Yeah. Another point. For US-based transport stacks, they must re-implement all layers of networking stacks in their US-based stack. However, this is also a key difference between eTran and other US-based transport stacks, because eTran can leverage these existing kernel infrastructures.
Okay, thank you.
Okay, cool. Well, my takeaway is that as you can leverage the kernel features, so it can do much more things than the user space network stacks, right? So okay, we have another question. Given multiple congestion control algorithms coexist in the public cloud, will there be challenges at the physical network switches? For example, due to compatibility issues? If yes, are there any existing solutions?
Yeah, I think this is a very challenging question, because it is out of the scope of eTran. Yeah, coexisting different transports with different congestion control algorithms is very challenging. Yeah. Qingkai, any thoughts on it?
I think it's a question that how to deal with a multiple congestion control algorithm coexist in public cloud. I don't, yeah, I can't, it's hard to say, but for, are you saying, would there be challenges at the physical network switch? I think they only have the, like performance, cause some performance issues when different congestion control algorithm coexist. But for the physical network switch, I think they can coexist, but only the I think the performance maybe the performance issue, like what we I think there is a paper named EQDS, and they showed how TCP and RDMA coexist, and they find some find there would be some performance gap between TCP traffic and RDMA traffic. I would say there would have some cause some performance issues.
Yeah,
And
EQDS shows that TCP and RDMA can work together where. Yeah. Go ahead.
Yes. So I think it's it's hard to it can coexist, but maybe just related to the performance issues. And I have no idea how to make them coexist well. Yeah.
Feel free. That's a good question.
Yeah, that's a good question.
Okay, so I actually have another question regarding the limitations of eTran. Yeah, we all know that by using eBPF, eTran can have the advantages of both user space designs, user space optimizations, and kernel security, kernel level security. So I'm just curious, what does it sacrifice so that it can gain such flexibility in kernel stack customization? Or what is the fundamental limitations of eTran?
Yeah. If I understand correctly, you mean the trade-off made by eTran. I think the complexity of implementing transport is a trade-off made by eTran. Yeah. Write eBPF code is actually a very not a very is not a very easy process because there are many constraints in eBPF verify. And for example, there is a instruction limit size, and you cannot use an unbounded loop. And there are many very tricky cases I have encountered before. So I think, yeah, eTran sacrifice the complexity of implementing transports. In addition to the complexity of implementing transports, yeah, I think kernel modification is another trade-off made by eTran. Yeah. Initially, we tried to implement everything in kernel, but we found it is very challenging and even impossible. So we finally decided to introduce new hooks to implement this. I know no kernel modification is a very appealing attribute, but eTran does need to make this trade-off.
Yeah, cool. My takeaway is that because eTran use eBPF, it encounters many limitations from the legacy eBPF, right? For example, the loop, right, and the fixed data structure. I think eBPF only supports some kinds of maps, right? So yeah, so it doesn't have the flexibility of using similar to the kernel code, right? Okay. Following that question, we have another one in the chat box. Has eTran encountered any new safety verification challenges compared to existing verifiers? Or the verifying processes of eTran's new program types are exactly the same as those of XDP?
Okay, good question. Actually, this is a design goal of eTran. The design goal is to make the kernel modifications needed by eTran is minor and simple to verify its correctness. So we choose to reuse many data structures, input contexts, BPF helper functions already implemented in the XDP. So if you look our XDP gen and XDP egress interface, you can see that its input context is exactly the same as XDP, and it can also call many BPF helper functions you can use in the XDP. So I think we didn't introduce any complexity in the eBPF verify to implement these new hooks.
But just out of curiosity, so I think for in NSDI 25, there's another paper from Shanghai Jiaotong University, right? I think that the system is called VEP, right? It talks about, it proposed a two-stage verification framework for eBPF programmabilities. So have you tried to use VEP to verify eTran, or eTran is just by design safe? It's from, I think VP is from Shizhen Zhao's group, right? You guys are friends with Shizhen, so you must know of that, right?
Yeah, I talked with him before. Yeah, I think eTran is safe by design because because the new hooks in eTran are all processed by the legacy XDP verify. There is no need for us to add a new verify logic for these new hooks.
I see. Interesting. Yeah. I'll ask Shizhen to next time I see him, see how he responds to this. Yeah.
Okay, wonderful. Does anybody has other questions? Because we are coming to the end of today's meeting. Okay, cool, wonderful. Okay, the time is almost up. It's over 12 o'clock. So a big thank you to Yao for the wonderful presentation. and also to Zhongjie and Qingkai for joining us to discuss their great work and sharing to share their experiences in design and implementing this this work. It was great having you here. So this paper actually brought up a lot of discussions and interesting points, and it definitely gave me a lot to think about. So thank you all again for joining today's reading group. Hope you enjoy it and got something out of it. Maybe for after 2 weeks, we will have our new SIGCOMM reading group, and maybe we will discuss a new SIGCOMM paper 2025. All right, that's it for today. Good night and have a good day. See you next time.